Hi everyone, thanks for coming to this presentation. My name is Jeff Taylor. I'm a PhD candidate at Utah State University, and I'm presenting today a characterization of the Common Research Model Wing for low-fidelity aerostructural analysis that I've been doing as part of my research. So you're probably familiar with the CRM. It's a outer mold line geometry meant for the validation of CFD studies, and it's shown here on the left. And for this paper, I also took information from the UCRM9 model, which is provided by the MDO lab at the University of Michigan. And the UCRM9 was designed for aerostructural studies, so it's a natural source for information in order to develop a low-fidelity aerostructural model of the CRM. So I'm going to be taking data from both of these, and this data is consistent, and some of it's the same. So. Key data for the CRM is given by Vasberg in the inaugural publication, but what's shown here is the extent of that data. So it's not sufficient to form a model from scratch. So in other words, I'm doing low fidelity work here, and I don't use a mesh. So a CAD file or an outer mold line geometry isn't sufficient for me. I need to have information about the geometric properties of that geometry in order to construct it myself in my analysis framework. So I'm using a numerical lifting line method. You could also use a vortex lattice method or other low fidelity method. And the goal of this paper is to provide enough information that you could import the geometry yourself without having to extract it yourself from the CAD model or from the finite element models. So the wing properties were extracted from the CAD model, the outer mold line of the CRM and UCRM. These are shown here in these figures. So what's shown is the chord, the twist, the sweep, and the dihedral angles. And you can see there's difference in the twist and dihedral angles between the CRM and the UCRM geometry. That's because the UCRM geometry is designed to represent the 0G loading condition, and when deflected or when loaded at a 1G cruise condition, it reproduces the original CRM geometry. So in its undeflected condition, it's different than the CRM geometry in these ways. The airfoil profiles were also extracted from the wing by taking intersection planes of the CAD model perpendicular to the projection of the locus of quarter chord points in the YZ plane. So that's like looking straight down at this top left figure, or top right figure. And you can see I've taken the planes perpendicular to that locus of points. Some example airfoil data shown here at the bottom. I found airfoil data for the lift, moment, and pitch coefficients using a transonic small disturbance theory and integral boundary layer method that's presented by Fujiwara. And that data is available. The code is not available, unfortunately, but the data is available to the reader at the Utah State University Library, Utah State University Library repository, or also through our website aerolab.usu.edu. The wing box properties were extracted from a finite element model of the UCRM9 wing box. So I was able to extract the front and rear spar heights and thicknesses for the front rear spars, the upper and lower skins, and the ribs. I was also able to extract center of gravity information from the finite element model. This was just taking the coarse mesh provided by the University of Michigan for the wing box and importing it into ANSYS Mechanical, and the result is shown here. The elastic axis, obtaining the elastic axis from a finite element model is beyond the scope of this work. I'm not an expert in FEM finite element analysis, but what I understand is that this is a very involved process. So I left that to others. There are a few previously published studies on very similar wing boxes designed for the CRM, and I've presented them here in this paper along with an average. So the reader can go through and choose which one they like and which one they want to use. The flexural and torsional rigidity were also taken from previously published data from a study that involving aerostructural optimization using the UCRM geometry. I developed a fuel model that's based in part on notional drawings of the 777-200 fuel tank layout and fuel information given by Boeing. This is all publicly available data, and the result is the weight distribution and the tank layout shown on the right. The weight distribution on the bottom includes the weight of the engine, which is why there's a spike. Fuel is first burned from the center tank and then from the wing tanks, so that you can get a change in weight distribution over time. And finally, here's a weight breakdown of the UCRM. This is taken from information from the University of Michigan and from Boeing. So here's a summary of everything, including key parts and where they came from. I'm not going to go through each one in detail for the sake of time, but if you want more details about this, be sure to look at my paper. There's a lot of data there. Some of the data is presented there, and some is provided, there's links provided to other data, including airfoil profiles and airfoil lift, drag, and moment coefficient data. So just to give you an idea of what I want to do with this. So the purpose of this paper was to have a publication with all this information so that next time I need to do something, I don't need to go and extract it, or so that other people who would like to do low fidelity analysis on the CRM don't need to go and extract this data themselves. It saves a lot of time and a lot of effort. But what I want to do with a low fidelity CRM model is what I plan to do as part of my research is a combined aerostructural and trajectory optimization of the CRM wing equipped with a distributed flap system, or in other words, a morphing system. And that's kind of expressed here. So you can imagine that this will require a whole lot of calculations. Every time that a calculation is done, there needs to be an aerostructural analysis involved to get the correct deflection at that loading condition. And so it requires a lot of computation, and so it's well suited for a low fidelity study because these computations can be done quickly, and you can get kind of notional information about the benefits of morphing mechanisms for aircraft fuel burn, including their effect on the optimal trajectory. So this is still in its early stages. If you have ideas on how I could do this, I would really appreciate it. I'm still working through that, but I hope that this low fidelity CRM model will facilitate studies like this for both myself and for others. Thank you for your time. I look forward to any questions. And if you don't get a chance to answer your question, if you don't get a chance to ask your question, feel free to send it to the email that's shown here. Thank you very much.